Yesterday you guys did this lab of a block moving on an incline, and you were basically just trying to find friction, but there's some other stuff going on in here, and I want to make sure you guys understand that. Okay, and so I'm going to draw this free body diagram and discuss some of these equations. Okay, first, anytime we start any kind of problem that involves force, we really should draw the picture, the free body diagram. Okay, so you guys had an incline, and it was inclined at some angle theta, and you had a block sitting up here, and you increase the angle until the block just barely started to move. So the block is going to slide down the ramp this way. Now there's several forces that act on this block. Okay, the first and foremost force that acts is the force due to gravity, and I don't like the way I drew that. Okay, gravity is always going to pull straight down. Okay, it doesn't pull into the ramp; it pulls straight down. The normal force, so this is the force due to gravity or the weight force. The normal force is always going to be perpendicular to the surface. Okay? The surface pushes perpendicular on the object. And then the frictional force always opposes motion. Okay? So this is the normal force. The frictional force, since it's opposing motion and this block is trying to slide down the incline, the frictional force is up the incline, and it's static friction if it's the one that's going to be overcome to just start the block moving. Okay. Now the vector sum of all these forces, vectors can only be added if they're in the same direction or if they're in opposite directions. Otherwise you've got to find their components and add components. None of these vectors are in the same direction. Okay. And so this is the free body diagram, but we've got to get a little bit more to this, which is what number 2 is all about. It says find the x component of weight. Well, to have an x component, I need an x direction. Okay, and when we do that, we usually set it up so that x is down the incline and y is perpendicular to the incline. And the reason for that is when this block slides down, okay, it's going to be moving only in x instead of in x and y, because x is slanted to match the incline. If we kept x and y straight up and down and straight left and right, then this block would accelerate not only in x but also in y, and it just makes the math a little bit harder. So we're picking our reference frame to make the math easy. Okay, now here's the cool part about this. Okay, when we do that, that means gravity is the only force here that's not pulling in an x or y direction. So we have to break gravity up into its component forces. Okay, and so this is FGY. It pulls this way. And this is FGX, and it pulls down the incline. Okay, this is a 90-degree angle because it's our x and y forces. Now, the angle theta right here, okay, is also the angle theta right here, and you can prove that using similar triangles if you'd like, but you can just assume it. Okay, those two angles are the same. It says, what equations will you need to find the x component of weight? Well, the x component of weight is the x value of gravity right here. Okay, and so we're looking at this side opposite the angle. The sine of the angle is equal to opposite side, which is the force of gravity in the x direction, over the force of gravity, the hypotenuse, opposite over hypotenuse, which tells me FGX, just rearrange this equation, is equal to FG, force due to gravity, times the sine of theta. Okay. Y component of weight, similar process, only instead of using sine, we're going to use cosine because we're looking at the adjacent side. So adjacent FGY over hypotenuse FG equals, or implies that FGY equals FG cosine theta. Okay. The normal force. Well, what can we say about the normal force and the force in the y direction? Since the block's not coming up off the ramp or accelerating down through the ramp, the net force in y equals 0. So we can say the normal force minus the force due to gravity is equal to 0. So we can basically say the normal force is equal to the force due to gravity. They just pull in opposite directions, but this isn't the entire force due to gravity. This is only the force due to gravity in the y direction. So the normal force is essentially the opposite of FGY. And finally, the frictional force. The frictional force is the static friction force, and it's equal to the normal force times the coefficient of static friction. However, okay, the normal force is really just Fg y cosine theta. Okay, so keep that in mind. If the block is motionless, what can we say about the forces? Of course, the forces are balanced. If the block is moving at a constant velocity, the forces are still balanced. It says, in a previous lab, we calculated a value for the coefficient. And we did. It was 0.234. At what angle will the block just begin to slide? Okay. Well, if you know this, then you can find the normal force or the frictional force, and then you can find the angle. Okay. And so essentially what I have is net force equals mass times acceleration, and I'm looking for the part where this thing just begins to slide. Of course, I'm only worried about the x direction, and there's only two forces in the x direction. There's Fgx minus the frictional force Fs has to equal ma, and this is just when the block begins to slide. So essentially what we're saying is Fgx has to be, see, if a is not going to be 0, if this is actually going to be a little bit more than 0, then Fgx has to be greater than Fs, right? That way we get a force instead of 0 force. And so then it's just, well, Fgx was mg, right, force due to gravity, times the sine of theta is greater than the static frictional force, but that's the normal force, which was mg cosine theta, times the coefficient of static friction. Okay. Now I want to know, and I know this. I'm trying to find the angle. Okay. So what I'm going to do is I'm going to go ahead and divide both sides by mg. Cancels out, and then I'm going to have the sine of theta is greater than mg, or not mg, just cosine theta. Okay, mu s. Divide both sides by cosine theta, and I get the sine of the angle divided by the cosine of the angle is equal to the coefficient of static friction. But that means the tangent of theta, if I jump over here, so let's just extend this page, that means the tangent of theta is equal to mu s, which is 0.234. So since I want the angle and I know the number, I just got to use the arctangent. So inverse tangent of 0.234 equals theta. Okay. The next page of this lab is basically do this. Find the angle at which the block begins to slide and see what you get. Okay, so 3 trials and an average, just to make sure we're eliminating error. The average angle is going to be used to calculate the static friction. And then number 4 is to show that the tangent of theta is, okay, well, we just did that on the other side. And how could you use a similar process to measure the coefficient of friction? Whatever you'd like there. Okay. Hopefully that clears some things up. If it doesn't, let me know. But you're also going to do another lab today that's similar to this, only with a car.